Okay, welcome back. This is part 4, a typical radiation day. Again, let me find my pointer here. Okay, so let's imagine how this works out over the course of a day. Let's imagine a day sort of like we have right now a lot, where it's clear and sunny, no clouds, that sort of thing. Like a clear and sunny day and a clear and cold night. All right. Lots of lines on this chart, but imagine again a typical fall day here in the mid-latitudes. Let's take this apart. Let's first of all look at this yellow curve. Well, this is how much electromagnetic radiation arrives from the sun. And this makes sense as the sun rises, right? We get heat from the sun, and it peaks around noontime, when the sun is highest in the sky, because you have the steepest angle of incidence, the steepest sun angle. And then it drops off through the afternoon and eventually becomes zero when the sun disappears. So this is what we call incoming shortwave solar radiation over the course of the day. In red, we have the reflected solar radiation. And that makes sense, right? That increases sort of parallel to the incoming solar radiation. This reflection is straight up reflection, let's say, from lakes and oceans and snow-covered areas. So now we have to think about the green curve and the blue curve. So the green curve is, the scale here goes negative because it's a cooling mechanism. It represents an energy loss for the Earth. And this is the surface of the Earth and the atmosphere emitting electromagnetic radiation into space. And that increases over the course of the day as the surface of the Earth heats up, heated, of course, by the sun. The surface of the Earth gets warmer. Therefore, it emits more long-wave radiation. And it drops again to lower values as the surface cools down into the night and through the night. And then we have the blue line, which is the amount of long-wave radiation that the atmosphere sends back to the surface of the Earth. And that's relatively constant because the temperature of the atmosphere is pretty constant. And the only weird thing is that increase here at night, which is presumably because some clouds came in on that particular night. So now when you look at everything added together, you get that orange curve. During the daytime, we have a positive energy balance. The Earth overall is gaining heat. The Earth is overall gaining energy from the sun, and it's warming. At night, the energy balance, the radiation balance is negative. Right? It's below zero here, it's negative. That means the Earth is cooling because it's losing energy. So that's how this plays out, if you will, over the course of a single day. We can also look at a single day in terms of when the warmest day, or the warmest time of the day is. Right? So we got midnight, 6 in the morning, noontime, 6 in the evening, and midnight again. And if there are no clouds, if it's a purely clear situation, minimum temperature happens here, and maximum temperature happens in the afternoon, which is a little bit odd. You'd initially think that the hottest or the warmest time of the day is at noon, because that's when the Earth receives the most heat from the sun. But of course, the atmosphere is primarily warmed from the Earth's surface. So you have to add together what happens to the outgoing long-wave radiation that the Earth emits and what comes in from the sun. And when that reaches a maximum, you get maximum heating of the air and you get the warmest air temperature. When you think about that, well, it makes sense, right? Outgoing Earth energy increases slowly. Sun comes up, heats the Earth's surface, and as the Earth's surface warms up, it sends out more and more energy until there's a point reached, because solar energy is dropping again, that the heating of the Earth's surface decreases, and when both added together reach their maximum value, you get the greatest heating of the atmosphere, and you have the warmest time of the day. So typically the warmest time of the day is not around noontime, even though that's when the sun angle is the highest. That's when the sun provides you the most heat. It happens typically at some point in the afternoon when we add together and reach a maximum, when we add together the energy from the sun and the energy emitted and absorbed by the atmosphere from the Earth. Now, we can also think about this at night. So here we have your classic situation, right? Imagine you have a beautiful clear night, no clouds, you can see the moon, you can see the stars, and those nights tend to be really, really cold. Contrast that, for example, with a night that's overcast, where there's clouds in the sky. Those nights tend to be much warmer. Right, we're taking the sun out of the equation. The sun isn't up. We're not getting any electromagnetic energy from the sun. So all we're dealing with now is the long wave radiation that the Earth sends into space. And if you have a clear sky, right, the Earth emits electromagnetic radiation into space, and all of that, or most of that, just travels through the atmosphere and is lost into space. That makes the Earth's surface the coldest. Now you put clouds into the sky, you add clouds to the atmosphere, you're effectively increasing the greenhouse effect by that, right? Because clouds are part of the greenhouse effect. So now a lot of that radiation that leaves the Earth's surface does not go into outer space, but instead is trapped, like with a blanket, if you will, and those clouds send it back down to the Earth's surface, and it stays much warmer. That's, in a nutshell, is the greenhouse effect. So when it's nice and cold outside, you can see the moon, and it's cold, you can see the stars. The greenhouse effect isn't that strong because there's no clouds. If it's overcast, greenhouse effect is stronger because clouds are there, acting as an additional blanket. So there you have it, part one of the Earth's radiation balance. We started very big picture. We started with thinking about this whole thing, sun, atmosphere, and Earth as a system. The idea that the amount of energy coming in has to equal the amount of energy going out. Then in part two, we learned about electromagnetic radiation and the fact that the Earth is emitting electromagnetic radiation, even though we can't see it because it's in a wavelength that our eyes can't pick up. That's our cooling mechanism. Now we put this all together, incoming heat from the sun, outgoing heat, if you will, from the Earth. That's our balance and all the processes and interactions that happens inside the atmosphere. And then we looked at a typical radiation day. Typical clear sky, clear sunny day, clear night. So the main figure I showed, figure 417 rather, that's you have that as a handout, right? And it's also linked. You also have a worksheet that's due on Wednesday. We will, of course, pick this up again on Wednesday. We'll review this on Wednesday. I have a little exercise for you to do in class as well. And then we'll add a few more wrinkles to this in terms of how this plays out for us, depending on where we are on the planet. And then on Friday, we'll discuss in more detail the greenhouse effect. And then, of course, on Monday, the 21st, a week from today, we'll run the third test. So there you have it, Earth radiation balance, part one. And what I would suggest you do now is a little reflection, because obviously this was a huge amount of material. There was certainly a lot of confusing things. There was some interesting stuff. And maybe you have a burning question you need to answer. Obviously, you can't share it with your neighbor right now, but still, take a few minutes and write these things down. The simple act of writing these things down already help you in your learning process. And then maybe go into your textbook, look at some Wikipedia, see what you can find to help you with some of those confusing things and these burning questions. So that's the end of this online lecture, right? Part 4 is over. We will see you again on Wednesday, and have a good one.